Okay, so let's continue with naming our chain alkanes. We went over the rules and we'll continue. So again, usually the first step is to identify the longest chain in the structure, and the one in black should be the longest chain. It doesn't have to always go straight left to right. It can meander. You have to track it. So let me try and number this 1, 2, 3, 4, 5, 6, 7, 8, 9. Already. Alternatively, you can number it from the top. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. So this is assuming that that's the longest chain, but still you have this other option here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So instead of going up, now we are going across. Alternatively, we can number it the same molecule. We can number it starting from here. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now, which of these one is the correct numbering? So there is one more rule that states that when there's competition between two parent chains, one has to take the numbering that takes the greatest number of substituents. So if you look at this one, whichever way you number it, you'll always end up with 3 substituents, but this one has 4 of them. You see, there is 1, 2, 3, 4. So this is the correct structure with the longest chain identified. So under this, now you have to decide, because this is gone, it has only 3 substituents, this has 4. Both of them have 9 carbons on the longest chain. This one has 4 substituents, so we go with this versus this one, which has 3. So under this, which is the correct number, in the blue or the red? Let's see. So based on the red, we have a substituent on 3, and we have a substituent on 4, we have a substituent on 7, and we have a substituent on 8. Sum all these up, you're going to get 22. Remember, we are going with the least sum. That's going to give us the least locations of our substituents, which is one of the rules. If in the blue, for the blue one, if you sum the substituent locations, you're going to get, there's a 7, there's a 6, and there's a 7, there's a 3, sorry, here, and then there's a 2. If you sum them up, you get 18, which means that this is the blue numbering is the correct one and not the red. So disregard the red. We've just proved that the blue numbering is the right one. Okay, so the name has to go with alphabet rule. So ethos come before methos. So we start listing the ethos first. The ethos are on 3 and 6. So we write 3, 6. There are 2 of them. So we say di, etho. So we don't go compare D and M, compare E and M, because E is under the actual name of substituent, not D. And then, so after writing 3, 6, di, etho, there are 2 of them. We use a hyphen to separate the alphabet from the numbers. And then the methyl is on the 7 and on the 2. So we write 2, 7, and then hyphen, then dimethyl because there are 2 methyls, and then non because there's 9 carbons. So again, this rule, just to repeat, this rule emphasizes that whenever you have a problem of identifying which is the right numbering system, go with the one that maximizes substituents. So instead of going this way, we went through this way. Okay, so let's continue here with more examples. So if I were to give the UPAC names, IUPAC names for these structures, I would count 1, 2, 3, 4, 5. There's no branch. You can number from the right to. So it's 5 carbons, so it's pent. And then all single bonds, N. Remember there's a CH3 here. There's a CH2 there. There's a CH2 here. There's a CH2 there. And there's a CH3 there. You just know that each carbon must have 4 bonds. That's how I know how many hydrogens are implied. Okay, this one 1, 2, 3, 4, 5, 6. So it's hex, all single bonds, A and E, suffix name. 1, 2, 3, 4, 5, 6, 7, 8. So it's an oct N. Now where there's substituents, now you have to be careful. You have to make sure that first identify the longest chain. This could be 1, this could be 1, 1, 2, 3, 4, 5, 6, and 7. And you have the other option of numbering from the left, which will be 1, 2, 3, 4, 5, 6, 7. So in red, I have a substituent right here, a substituent right there. So I have the substituents at 3 and 6. I sum it up, I get 9. In blue, where's the blue? So in blue, I have a substituent on the 5 and 2, so 2 plus 5, I get 7, which means the blue numbering is the correct one because it gives you the least sum of the location of the substituents. So the red numbering is wrong, we ignore it. Now we focus again on the substituents. This happens to be a methyl. This happens to be a methyl. So the name should be 2, 5, going with the blue, 2, 5 hyphen, there are 2 methyls, so di, methyl, and then the longest chain has 7 carbons, hept, there's no pi bonds, so A and E, heptane, 2, 5 dimethyl, heptane. What about this ugly structure? Let's see, the longest chain will be, if we count straight ahead, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or you could say 9, 10. Whichever way you go, one of them will be a substituent. What about if you start from here in red? So I'm going to try all possible methods to find the longest chain. Let's do red. Okay, so it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So already the red is winning. So now we have to follow the track. We disregard the blue because it only has 10. We go with the red. So now I'm going to take another color. Where is purple? How comes I don't have purple? Let me use magenta. So what if I go 1, 2, 3? Now that I know this is the longest track. 4, 5, 6, 7, 8, 9, 10, 11. So between the red and the magenta, which is the correct numbering? So let's circle our substituents and then sum their positions. They will let us know. So you have an ethyl here with 2 carbons in. This is also an ethyl, there's 2 carbons. This shape is called isopropyl. Okay, if you've forgotten, this slide is very important. It tells you whenever you have a long chain, if these groups are popping out, you get those names. So what you're looking at here is this isopropyl. Okay, so come back here and we call this an isopropyl. So in the magenta, I have a substituent at 4. I'm going to sum it up, and then at 5 here, okay, at 4, and 4th carbon, 5th carbon, and then oh, there's one more substituent here. I have a substituent at 6. It's popping out of the longest chain, and then I have a substituent at 9. So if I sum all this up, I get what do I get? I think it's 24. Yeah, I get 24. Now for the red one, that has the 11 carbons in it, I'll have a substituent at 3, 6, 7, and 8. So 3, 6, 7, and 8. 3, 6, 7, and 8. Sum this up, it's gonna be what? 15 and 9. I'm getting 24. So there's a problem. So whenever there's a tie, let me make sure. Whenever there's a tie in the locate positions, one would want to go with alphabet rule. You go with alphabet rule. So you go with the alphabets of the substituents. Okay, so the name of this compound will be given based on the red numbering. So I see ethyl, I have a butyl. You have 1, 2, 3, 4 carbons in this substituent, right? There's an ethyl, there's a butyl, there's an ethyl, and isopropyl. So we'll start by in giving the name, you have to start by prioritizing the alphabets. So B comes before all these others. So we'll see that the B is on the carbon 6. So the name will be 6-butyl, and then a hyphen. So next we go to the E's. There are 2 of them on carbon 3 and 7. So it will be 3, 7, and then you say di because there are 2 of them, diethyl. And then next, of course, is gonna be now the isopropyl. It's on carbon 8 isopropyl. And then now all substitutions are taken care of. So next we go with the longest chain, which has 11 carbons. Of course, we are going with the red numbering. So that will be un-dec. That takes care of the 11 carbons. And then there's no pi bond, so it's an alkane, N. So the correct name for this structure would be 6-butyl 3,7-diethyl 8-isopropyl undecane. Always consider the alphabets whenever you're writing the official name. We don't consider di, tri, and anything that's in italicized. Okay. All right, you practice. Okay, so again, to summarize, you need to identify the parent chain, identify the substituents, assign the locant position of the substituents, giving them the least number position on the longest chain. If the numbers of the carbons on the longest chain are giving you the same answer when summed up, like what we did here, then you will take the numbering system that gives you the that goes with the alphabet rule. So if the locant position ties, if there's a tie, use the alphabet rule. Prioritize the numbering system that encounters the least alphabet in ABCD, EFGH. And then lastly, you name the compound based on alphabet rule. Remember, like here, we named the compound this way because B comes before E and I. So this is done for you. Simple as that, you can practice it. So next, let's talk about constitution isomers. Remember, these two molecules, both of them have the same chemical formula C4H10. Both of them have the same chemical formula C4H10, but they are drawn differently. Actually, you should know that there's a CH3 here. There's only one bond to the carbon, so 3 are not shown, which goes to the hydrogens. There's a CH2, there's a CH2, and there's a CH3. At each end there must be a carbon. So if I am to really draw this isomer found from what we call butane, I have to swap groups. So I'll take a part of the chain like this one and swap it with the position of the hydrogen. So these two groups are interchanged. You don't want to swap with the hydrogen here. You have to go one carbon over. So if you do this swap, you're going to end up with the CH3 right here, and the hydrogen will come here. Remember, you already have two hydrogens here. You're just switching the position of these two guys. So the metal ends up there, this hydrogen ends up here. You still have the two hydrogens here. So this structure right here is actually that without showing the hydrogens. So butane only has two isomers, the normal butane, and I think if you were to give the UPAC name for this one will be 2-methyl propane, 2-methyl propane, because this is the substituent, the methyl on the second carbon. Now, constituent isomers are different because of their physical property. In fact, whenever you do branching from a straight chain, the boiling point, the melting point will decrease because the surface area of contact is decreased. Between these two molecules right here, there's more intermolecular forces, IMFs, what we call dispersion forces or weak van der Waals forces. Those ones tend to bring the molecules or bind the molecules together. But the moment you branch it, now the longest chain is shorter. There's less contact. Just like your arm. If you put them straight ahead, okay, there's more contact. But once you branch it off, there's going to be less contact on the longest part of your arm. So that's what this is saying. So this molecule, when two of them come together, they will have a lower boiling point, melting point compared to this one, which is straight chain. So here you have less intermolecular forces, what we call IMFs of contact. Here you have more, so the boiling point here will be less than the boiling point here. Okay, because you are decreasing the surface area of contact of the intermolecular forces. So in other words, simply put, branching decreases boiling point and melting point due to decreasing surface area of intermolecular London dispersion forces. Okay, so to prove that you'll see that butane has a boiling point of 0.5, and 2-methyl propane has a boiling point of 11.6. Sorry, let me repeat. To prove that, you'll see that butane has a boiling point of negative 0.5. 2-methyl propane has a boiling point of negative 11.6. Obviously, this is higher boiling point than this one, which is lower, it's more negative. So branching decreases the surface area. of the intermolecular forces in this case, because there's no electronegative element in the structures. You only have London dispersion forces. So the number of isomers vary. I already mentioned this when we started. So the first time you see isomers is in a structure with 4 carbons. We just talked about butanes, which this will happen to be the 2 isomers. Pentanes will have 3 isomers. Hexane will have 5 isomers. Heptane will have 9 isomers. Octane will have 18. 13 carbon will have 8 or 2. If you have a 30 carbon structure, that one will give you more than 4 million isomers. So let's practice one more practice, I think, using hexane. Let's find these 5 isomers. How do you find them? So like I did, I'll choose a substituent and I'm gonna just specifically show it, and then I'll swap it with a hydrogen on 1 carbon over. So let's interchange these 2 guys. We're gonna end up with 5 carbons because I chopped 1 off. 1, 2, 3, 4, 5, 6. That's why it's hexane. So now you're gonna end up with 5 carbons. 1, 2, 3, 4, 5. The metal ends up on carbon 4, and this hydrogen will end up on carbon 5. Remember, carbon 5 already has 2 hydrogens, so now you're gonna end up with 3 hydrogens. So really, this one shown without the hydrogen should look like this. So that's the first isomer. You still have the formula C6H14 in there. All these isomers will have the formula C6H14. If you count and show the hydrogens, there will be 14. Now to find the next isomer, I'll use this structure here. Okay, I'll use it to branch it. So I'm gonna choose this method this time around and swap it with a hydrogen 1 carbon over. So let's interchange them. So I'm gonna now I'll end up with 4 longest chain, so to speak, and then this method that was here comes here. The hydrogen that was there goes where the metal was. You are changing their positions, you are swapping them. So remember, you have 2 hydrogens here. Which are these hydrogens here where the metal originally was? Without showing the hydrogens, this will be the structure, and that is the 3rd isomer. To get the 4th isomer, I use the 3rd isomer. So this time I'm going to swap this hydrogen right here. It's there. This carbon must have 4 bonds, so there's an implied hydrogen, which is this. I'm going to swap that hydrogen with the metal. So interchange the position of groups on neighboring carbons. So doing that, of course, we have a hydrogen here. Doing that, we're going to end up with this structure. So the hydrogen that was moved will be there. This hydrogen was originally there, it's just this hydrogen. And then the metal goes in between these 2 metals. So without showing the hydrogens, this will be the structure with what looks like a butyl group. Okay, that's the 4th isomer. Now the 5th isomer of hexane can be found by, I think we need to go back to number 2. Let's see. Yeah, let's go back to this structure, isomer number 2. So I'm gonna move this CH3 from here and swap it with this hydrogen. So I have the longest chain with 5 carbons, and then I'm moving this CH3 right in the middle. Okay, and then this hydrogen goes where the CH3 was, which is here. Remember, again, we already have a hydrogen there to make 4 bonds around the carbon, so that's the hydrogen I'll show here. So this will be the 5th isomer. Without showing the hydrogens, it's gonna look like this. So that's one isomer That's the second isomer. Of course, this is an isomer in itself. Third isomer, fourth isomer, and the fifth isomer. So that's the process of finding isomers. Practice how to find the 9 isomers in heptanes. So next, we'll talk about physical properties of hydrocarbons.